So for question number 1 here, it's asking us who originally proposed the idea that all matter could be made of atoms. Democritus, yeah, okay, the Greek guy. Okay, he said that could be the case. But his idea wasn't very well accepted because the Greeks already had a system in place. Okay, and that system in place was that everything was made of 4 elements, and everybody knew that. Okay, and so they said, yeah, that's not such a great idea, and it kind of just got left on the wayside because they had something that made more sense at the time. Okay, it wasn't that either one was like proven in any way, shape, or form, but okay, the other one made more sense. The four elements. Okay, for number 2, what were the 4 elements? They were earth, air, water, and fire. Okay, those were the 4 elements. Okay, and it made sense. It was logical. They could, they could figure out how much of something was earth and how much of it was fire or air or whatever. Okay, the example we used yesterday was that steam was some parts water, some parts fire, and some parts air. Okay, and they kind of had, ratios or whatever for things like that. Okay, question number 3. In the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. Okay, who were they? What did we call them? They were the alchemists. Okay, and their goal was to do things that we now know are impossible, like transmute lead into gold and things like that, or develop the elixir of life. Incidentally, you did not want to be like their test dummy. Okay, when they were testing their elixirs, because they had things like if you drank mercury, that would make you live forever. Except it does the exact opposite. It makes you poop chrome and die early. Okay, so yeah, you wouldn't want to do that. Okay, necessarily. So, okay, number 4. In the late 1700s, a man used the data from many experiments on matter to develop an idea on its structure. Okay, so who was that? John Dalton. All right. He had 4 points to his atomic theory. Make sure you have these written out somehow in your own words. Okay. The first point was that all matter is made up of tiny, indivisible particles called atoms. The second point of his theory was that atoms of the same element are identical. Atoms of different elements are different. Okay. Third point was that atoms can combine with each other in whole number ratios. That's the most important part of that it's always whole numbers, okay, to form compounds. The example we used yesterday was hydrogen reacting with oxygen to form water in a 2-to-1 ratio. It's never a half of an atom. Okay, it's never a fraction of an atom. Okay, and then the fourth point was that in a chemical reaction, atoms can be separated, they can be joined, they can be rearranged, but they cannot be turned into other atoms. Okay, I'm not creating anything I didn't have before in a chemical reaction. Question number 5. If we look at that theory now, what part of it can we say isn't necessarily true? Okay, so there are smaller particles. We know about, protons, neutrons, electrons. We know about quarks, all the different kinds of quarks and all that kind of stuff. Okay, but we also know that we can now do what to the atom? We can divide it. Yeah, we can split it. Okay, we can undergo nuclear fission. That is a process that can occur. We also know about radioactive decay, which is the natural breaking down of an atom into something else. Okay, anything that's radioactive naturally breaks down, loses particles. That's why it's radioactive. Okay, and turns into other things. Okay, over a very long period of time, uranium-238 turns into lead-237. Okay, it just loses particles and becomes something else. Okay, so it just naturally breaks down. Okay, looking at the models of the atom. The first model of the atom was Dalton's idea, and supposedly it looked like a what? The solid sphere model. Okay, so everything was just a ball. And we didn't know any better at the time. Kind of made sense, so we went with it. Okay, then J.J. Thomson came along and he discovered electrons, so he modified it to be which model? Plum pudding. Okay? It accounted for the fact that negatively charged particles were parts of atoms, and that we knew that because electrical current could flow. After J.J. Thomson, Okay, Chadwick discovered protons, neutrons, okay, things like that, and we discovered that there were more parts to the atom than just a solid central positive sphere and these little tiny electrons. Okay, then Rutherford came along, and he did the gold foil experiment. That is definitely something you'll need to remember. Okay, Rutherford's gold foil experiment is very, very important because it proved the existence of the nucleus. And then from there, we had Rutherford's model, Bohr's model, okay, and now de Broglie's model, which we call the electron cloud. Okay. All right. Then for number 7, okay, our knowledge increased. As our knowledge increased, we discovered the atom had smaller parts. So we already discussed those. We have protons, neutrons, and electrons. Protons are located where? Okay, they're around the neutrons, and protons and neutrons are in the same place, which we call the nucleus. Okay, so protons and neutrons are in the nucleus. Protons are positive, neutrons are neutral. Okay, electrons are in the cloud surrounding the nucleus. Okay, and they are negatively charged. One of the things that you will be asked to do in this course is draw me a picture of a particular atom. All right, so I would give you a particular one. Let's say I pick fluorine, for example, and I ask you to draw what an atom of fluorine would look like. Right, so what I would need to do then is figure out how many protons fluorine has, how many electrons it has, how many neutrons it has. Okay, now this is something you probably learned in Science 9, but you may not remember how that works. All right, so on your periodic table, okay, which you got earlier this morning, you're going to see, let's look up fluorine. Fluorine is element number 9, so it's over on the right-hand side, okay, kind of the second row. And we can see in the box for fluorine, okay, we got a big F, okay, stands for fluorine. We got 19.00 up in the top corner, okay. We have the big number 9 here in the top left corner, and then we got a couple of other smaller numbers that aren't really important right now, okay. The number 9 is the atomic number for fluorine. The atomic number tells me the number of protons in the nucleus of that atom. So all fluorine atoms, without exception, have 9 protons in the nucleus. Now, for an atom to be electrically neutral, which they all are, the number of positives has to equal the number of negatives. So how many electrons are there in a fluorine atom? 9. Okay. Okay. How do I figure out how many neutrons there are? They don't have a charge. Okay. They're not part of this whole there's 9 protons, there's 9 electrons thing. Okay. Yes, it is something with the atomic mass. Okay. So this is the atomic mass of a fluorine atom. That is exactly what you do. You take the atomic mass, which is the mass not like of the whole atom, but of a certain number of them, okay, and we subtract the atomic number. That will leave us the number of neutrons. Okay, in this case, there's 10. Now, with fluorine, it works out nice because it comes out to like 10.00. Not every element is going to be like that. You could get a decimal afterwards, but it's usually very close to a whole number. Okay, either it's like 0.9 something or it's 0.00 something. Okay, you always just round to the closest whole number because you can't have a fraction of a neutron, right? If I was to say, let's say, get this answer to be 9.89, I wouldn't say there's 9.89 neutrons. I can't have 0.89 neutrons. It's a particle. I either have one or I don't. Everybody follow? So if I got that, I would say that there are 10. Okay, I would just round. There's 10. Okay, so in this case, there's 10 neutrons. So if I'm going to now draw a picture of the fluorine atom, sorry, this is how we calculate number of neutrons. Okay, so if I'm going to draw a picture of that, what I would probably do is draw the nucleus, and I'm just going to give myself a little bit more room here. Okay, so I would draw the nucleus, and I would make sure that the particles all looked a little bit different. I lost count, 8. Okay, there's 19 particles in the nucleus. There's 9 protons, and there's 10 neutrons. All right, so what I need to do is identify which ones are which. So I'm just going to randomly pick. There. Now I've got 9 protons. Okay, the ones without anything in them are neutral. They're the neutrons. Where do I put the electrons? Yeah, anywhere. They're in the cloud on the outside. As long as I don't put them in the nucleus, I'm okay. Okay, what I usually do is I just do this. And I draw like a cloud, and I just go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then I put a legend beside it. Okay, now that diagram is pretty clear, right? I know where everything is, I know what they are, okay, and I can count the numbers and see if you're right. Okay, so something like that. I would definitely ask that on a quiz or a unit exam. Is that a subtle enough hint? One of the questions on your unit exam? Okay, for number 8, okay, 1 cubic centimeter of lead is much heavier than 1 cubic centimeter of carbon. We're just going to assume there's the same number of atoms of carbon and lead in a cubic centimeter. There aren't, but we're going to assume that. Okay, so I have the same number of carbon atoms as I have lead atoms. Why is the lead so much heavier? Yeah, the lead atoms are bigger. Okay, again, if you look at your periodic table here, okay, if you look at the box for carbon, okay, carbon has 6 protons and it's got an atomic mass of 12.01. Right, so its atoms are fairly small. It would have 6 protons, 6 neutrons, 6 electrons. Lead, on the other hand, okay, its box is that we've got it's 82. So it's got 82 protons. It's got an atomic mass of 207.2, which means it's got a lot of neutrons. Okay, a lot of them, way more than carbon has. Right, so these atoms are just plain bigger. Right, if I have the same number of carbon atoms and lead atoms, there's going to be a lot more mass to the lead because the atoms have more particles. They're bigger. Okay, that's what makes them different. Okay, number 9 we talked a bit about yesterday. Nuclear reactors use atoms with very large nuclei like uranium, which has 237 particles in its nucleus. Okay, and we use that for fission. Why wouldn't we use smaller, less dangerous atoms like lithium that only has 7? Well, if I'm trying to hit a target, do I want a big target or a small target? A big target, unless I'm really trying to show off, okay? But I probably want a big target because I'm more likely to hit it, all right? So that's part of it. Hitting lithium atoms, they're really small, okay? But secondly, the smaller an atom is, the less energy it will release when I break it. So why not pick a big atom? It's going to have more energy in its nucleus than a small one, okay? So we want to use something that's big, that's already kind of unstable, and uranium is, okay, as opposed to something like lithium that's pretty happy the way it is, not looking to break down or do anything like that. Okay, and number 10 we talked about a minute ago. Atoms are indivisible. Okay, why was that statement believed for so long? Well, what could nobody do? Yeah, no one could split them. Okay, no one had any way to do it. Atoms were really small. Okay, you couldn't cut them physically, so there was no way to do that. Now, obviously, we know there is a way to do that. Okay, we're able to do that, and we release a fair amount of energy, but it's not something that typically happens quickly in nature. Okay, it does happen, but it happens very slowly. Okay, and that's what we call radioactive decay. Right? So there are some atoms that do decay and they release radiation, but they do so very, very slowly. All right, number 11. From what you know of the structure of the atom, how do you think the atom stays intact? Why do electrons not fly off or protons separate from the nucleus? Let's start with kind of the easier one. Why don't the electrons just fly away? Yeah, there's an electromagnetic pull towards the protons, right? Opposites attract. Electrons are the most negative thing there is. Protons are the most positive thing there is. They are naturally attracted to each other in the way that planets are naturally attracted to the sun's gravitational pull. All right, so that's part of the reason. Okay, now why doesn't the nucleus just fly apart? Well, if you put the most positive thing there is next to something neutral, that something neutral appears negative by comparison. Okay, and so they are attracted to each other, and there's this atomic force that holds the atom together. And when we break an atom, that atomic force is what releases nuclear energy. Okay. All right, and number 12 has to do with de Broglie's electron cloud model. We talked a little bit about this yesterday. Glow-in-the-dark materials, when light strikes them, their electrons become excited. And when they do that, they move from low energy levels where they're close to the nucleus. So here's my nucleus, and then here's the cloud. Okay? When an electron gains energy, it moves away from the nucleus. When that energy that's keeping it up here is gone, it'll fall back down in steps called quantum. Okay? As it comes down, it releases that energy. Glow-in-the-dark materials release that energy as light. In plants, this same process occurs, but it's in the chlorophyll molecule. The electrons move up, and then as they fall back down, that energy is harnessed, okay, by the organelles in the plant that carry out photosynthesis to make sugar instead. So instead of glowing, a plant uses that energy to make its own food. Right. Okay, questions on any of those? All right. Oftentimes there are things within here that end up on quizzes and unit exams. So you might want to refer back to this when you're doing some studying later.